Hello everyone, welcome to my YouTube channel. I am Deepak Prasad as studying at Sri Venkateshwara College of Engineering. Today's subject is physics. Subject code is BPHYS102 and my library ID is 23CA1558. Today's topic is variation of wave function and probable densities of a particle in 1D potential of infinite wall height. Coming to the introduction part of the topic, the particle in a box is a common application of quantum mechanical model to a simplified system consisting of a particle moving horizontally or also vertically within an infinitely deep well which has no chance to escape. I have divided this derivation into four parts so for your understanding. The first part is defining the potential energy V. So the second part is solving the Schrodinger's equation. Third part is defining the wave function. And fourth part is substituting the n values as 1, 2, 3 and 4 in the final equation which we acquire after this derivation. Getting started with the derivation, here's the step-by-step process discussed below. Step 1. Define the potential energy V. The potential energy is 0 inside the box where V is equal to 0, 0 is less than x and x is less than L and goes to infinity at the walls of the box. V is equal to infinity for x is less than 0 or x is greater than L. Now let us consider a free particle of mass that moves only along the x-axis and is confined between x is equal to 0 and x is equal to L by two infinitely hard walls, so that the particle has no chance of penetrating them. This is possible only if the potential energy is infinite at x is equal to 0 and x is equal to L or between 0 and L. This is known as the particle in a one-dimensional potential well of infinite wall height. Okay. At x is equal to less than or equal to 0, x is equal to and x is equal to L, V becomes infinity. At x less than 0 or equal to 0 or at x is equal to L, V becomes infinity. V is equal to infinity. Xi is equal to 0. We assume the walls have infinite potential energy to ensure that the particle has zero probability of being at the walls outside the box or the wall. Doing so significantly simplifies our later mathematical calculations as we employ these boundary conditions when solving the Schrodinger's equation. Step 2. Coming to the step 2, solving the Schrodinger's equation. The time-independent Schrödinger equation for a particle of mass moving in direction with energy E is minus h square by 2m d square xi by dx square v of x into xi of x is equal to E xi x. This is the required Schrodinger's equation with h is the h as the reduced Planck constant, m is the mass of the particle, v of x is the potential energy of a function of a position, E is the energy of a real number. This equation can be modified for a particle of mass m free to move parallel to the x-axis with zero potential energy. V is equal to 0 everywhere, resulting the quantum mechanical description for free motion in one dimension. Since V is equal to 0, we substitute V value here. So v of x into xi of x, 0 into xi of x becomes 0 and we get the final equation minus h square by 2m d square by xi into x divided by dx square is equal to E xi x. Coming to the step 3, defining the wave function. The solution to Schrödinger equation we found above the general solution for a one-dimensional system. Now we need to apply our boundary conditions to find the solution to our particular system. According to our boundary conditions, the probability of finding the particle at x is equal to 0 or x is equal to L is 0. Then B must be equal to fulfill this boundary condition, giving the equation xi of x is equal to a sin kx. We can now solve our constants a and k systematically to define the wave function. First, solving for k, differentiate the wave function with respect to x. We get d xi by dx is equal to ka cos of kx. Again differentiating, we get d square xi by dx square is equal to minus k square by a sin of kx. Since xi of x is equal to a sin k of x, then the equation becomes d square xi by dx square minus kx square xi. Now, if we then solve for k by comparing with the Schrodinger's equation above, we find k is equal to 8 pi me divided by h square whole power 1 by 2. Now, the general solution for the above differential equation, which we found in the last slide, is given by xi x is equal to a sin of kx plus b cos of kx. Call it as equation 4. Okay, the wave function xi of x should be 0 everywhere outside the box, since probability of finding the particle outside the box is 0. Similarly, the wave function xi of x must also be 0 at the walls of the box, because the probability density xi of x whole square must be continuous. Thus, the boundary conditions for this problem is that xi of x is equal to 0 for x is equal to 0, and xi of x is equal to 0 for x is equal to L. Now, applying the boundary condition for equation 4, at x is equal to 0, wave function xi of 0 is equal to 0. Now we get xi of 0 is equal to a sin k into 0 plus b cos of k into 0. Since we know that xi of 0 is equal to 0, substituting a sin k into 0 plus b cos k into 0. Now b becomes 0. Hence, substituting the value of b in the fourth equation, xi L is equal to a sin of kx. Now applying the second boundary condition, at x is equal to L, wave function xi L is equal to 0. We get xi of x is equal to a sin k into L. This equation will satisfy only for a certain value of k, say k. Since a cannot be taken 0, hence sin kn of L is equal to 0. Sin kn of L is equal to sin into n pi. Sin gets cancelled. We get knl is equal to n pi. Send L below. We get the equation kn is equal to n pi by L. Thus, for each allowed values of k, there is a wave function xi x. Using equation 5 and 7, xi n of x is equal to a sin n pi x divided by L. This is the expression for wave function or eigenfunction for a particle in a box. Now, from equation 3 and 7, we get k square is equal to 8 square me divided by h square is equal to n pi by L whole square. Using this equation, we can write E is equal to n square h square divided by 8 ml square. This is the required expression for energy or eigenvalue of a particle in a box or an infinite wall length. The general expression for this energy is written as E power n is equal to n square h square divided by 8 ml square. Step 4. Now, after doing all these steps, substitute n value as 1, 2, 3 and 4 in the given or derived above equation. For different values of n, energy values can be written for n is equal to 1. When n is equal to 1, n square is equal to 1. So we get the equation E1 is equal to h square by 8 ml square. It is known as 0 point energy or ground energy state. For n is equal to 2, E2 which becomes 2 square into h square by 8 ml square. This h square by 8 ml square can be written as E1. 2 square is written as 4, which is equal to, which can be written as 4e1. n3 for n is equal to 3. 3 square h square by 8m l square, which is equal to the same as the above. H square by 8m by l square is written as e1, and 3 square is written as 9, which also becomes 9e1. For n is equal to 4, e4 is equal to 4 square h square divided by 8m l square. The same as above, h square by 8m l square can be written as e1. 4 square is written as 16, which is equal to 16e1. Thank you everyone for watching my video. Hope you find this informative, and I will be meeting you soon with my next video. Thank you everyone. Take care.